Hey everyone, welcome to this explainer. Today, we're doing something a little bit different. We are going to completely redefine how you think about programming. We're going to shift the focus way away from all that intimidating syntax, those confusing screens of text, and all the heavy jargon. Instead, we're moving toward the truly empowering art of computational problem solving. If you've ever thought programming was just about memorizing computer code, well, prepare to have your perspective entirely transformed today. Okay, so let's set the stage with a really crucial idea right off the bat. At its core, programming is simply problem solving. Just like a writer uses language to convey ideas, a programmer uses code to translate human intentions into precise, executable instructions. It is fundamentally the art and science of instructing computers to perform tasks. The code itself, honestly, that's just the medium. The real magic, the actual heavy lifting, is in the problem solving. So that brings up a pretty massive question. How exactly do we translate what we want into something a machine actually understands? Because translating human intention is exactly what's happening behind the scenes of things we use every day. Think about mobile banking applications like MTN Mobile Money. It's what drives the traffic management systems keeping cars moving in Accra. And it's literally the foundation of agricultural monitoring platforms used by cocoa farmers in the Ashanti region. But how do we actually build these solutions? To answer that, we're going to walk through the exact chronological journey a developer takes to solve a real-world problem. We'll cover the art of problem solving, dive into core programming building blocks, control the logic flow, figure out how to manage complex data, look at algorithm design strategies, and finally, wrap things up in the developer's environment. All right, kicking things off with Section 1, the art of problem solving, also known as the blueprint phase. You know, the absolute biggest mistake a new programmer can make is just jumping straight to the keyboard. Don't do it. Long before writing a single line of code, you have to master this blueprint phase. Every computer scientist uses a universal four-step methodology to tackle a new problem. First, you start by really understanding the problem, pinning down your inputs, outputs, and constraints. Step 2 is designing a solution using human-readable pseudocode or visual flowcharts. Only then, in Step 3, do you actually implement the code. And finally, Step 4 is testing and debugging to make sure it actually works. Let's put this into perspective. Imagine a mobile money agent in Kumasi who needs a program to calculate daily commissions. Applying Step 1 means we have to look really closely at constraints and edge cases. Like, what happens if someone tries a zero-amount transaction? What about a failed transaction or a sudden network timeout? Listing out these specific edge cases before we write any code is absolutely crucial to ensure our design survives the unpredictable real world. Moving right along to Section 2, core programming building blocks, specifically looking at variables and data. So you've got your blueprint and you've mapped out the edge cases. Now what? Well, you transition to the actual building blocks you need to implement the solution. Think of variables as the nouns of our language. They're just named storage locations in memory that hold your data. You might use an integer for a student's age, a boolean for a simple true or false status like, has this student paid their fees? Or a double for decimal numbers, say a GHS to USD exchange rate. And of course, you've got strings to hold text like a person's name. Now, if variables are our nouns, operators are definitely the verbs. We use these to act on our data. We perform math with arithmetic operators, we compare values to see if one is bigger than another, we use logical operators to combine different conditions, and we use assignment operators to give new values to our variables. Basically, this is how we start manipulating all that data we stored in our nouns. Which brings us to Section 3, controlling the logic flow, where we start making dynamic decisions. Right now, even with our nouns and verbs, a program is just a static list of commands. Kind of boring, right? We need to tell the computer how to make dynamic decisions to bring those commands to life. Control flow dictates the order of execution. Conditional statements, like an if-else block, let a program branch its logic, like checking if a withdrawal amount is bigger than a user's balance, and printing insufficient funds if it is. Loops, on the other hand, handle iteration. You'd use a while loop to repeatedly ask a user for a PIN code until they get it right. As things get more complex, you definitely don't want to keep rewriting the same code over and over. To keep our logic organized, we wrap these instructions into functions, or methods. Think of a function as a custom, totally reusable block of code designed for one specific task, like calculating tuition based on credits, or figuring out a letter grade. By passing parameters into these functions, your code becomes infinitely more readable and modular. Next up is Section 4, managing complex data, or as I like to think of it, organizing chaos. Because let's face it, as mobile apps and databases grow, a couple of simple variables and functions just aren't going to cut it. Almost every program processes text in some way. Whether you're validating an email address or parsing CSV files for a bank, text processing is a huge deal. Developers use tools like regular expressions, often called regex, to strictly validate user input. For example, a regex pattern can ensure a user's phone number matches the exact local Ghanaian format, catching bad data before it even enters the system. There's also a massive paradigm shift in how we handle complex data. Think about a procedural approach, where data like a student's name, GPA, and program are just scattered everywhere as loose variables. It gets messy fast. But if you adopt an object-oriented mindset, everything changes. Your data and behavior are neatly organized together into a reusable blueprint called a class. So instead of loose variables, you create a cohesive student object. It makes managing complex systems so much easier. Let's dive into Section 5, Algorithm Design Strategies, which is all about solving problems at massive scale. When you're dealing with massive collections of data, we're talking thousands of student records or millions of banking transactions. Basic code just won't work efficiently. You have to employ high-level algorithmic strategies. You've got techniques like divide and conquer or greedy algorithms that make the locally optimal choice at every step. But then you have dynamic programming. This is a master strategy. It breaks a complex problem into overlapping subproblems and remembers the solutions, so the system never wastes time recalculating something it already figured out. It's incredibly smart. So why does this actually matter in the real world? Well, think about a logistics company delivering packages all across Greater Accra. They can't just guess the best routes. They use a combination of these exact greedy and dynamic algorithms to optimize multi-stop routes throughout the day. The result is they minimize their fuel costs and drastically slash delivery times. Algorithms are literally shaping the physical efficiency of our cities every single day. Finally, we've arrived at Section 6, the developer's environment. Let's look at the tools of the trade. We've reached the last step of our problem solver's journey, the actual environments where developers build and deploy these solutions. Different problems demand different tools, right? That's exactly why programming languages are categorized by paradigms, like object-oriented, functional, or scripting. In terms of industry focus, Python and JavaScript are currently the most in-demand languages in the Ghanaian tech ecosystem, powering huge companies like Hubtel and ExpressPay. Whether you're in web development, data science, or systems programming, picking the right language paradigm is absolutely critical. But let's be real for a second. Nobody writes perfect code on the first try. Logic, syntax, and runtime errors are completely inevitable, so developers rely on systematic debugging. You might use print debugging to track down values, or even something called rubber duck debugging. Yes, that's a real thing. It's the proven technique of explaining your code out loud to an inanimate object just to isolate a logical error. Developers also use try-catch exception management so that when things do go wrong, the program handles the error gracefully instead of just crashing the whole system. And where does all this magic happen? It's orchestrated inside an IDE, an integrated development environment. Tools like VS Code or IntelliJ are basically the ultimate digital workbench. They give you smart code completion and built-in debuggers. And when you pair an IDE with version control systems like Git to track your changes, developers can collaborate seamlessly on a global scale without ever accidentally overwriting each other's work. As we wrap up this explainer, I really want you to remember that memorizing syntax and learning a new language is literally just the beginning of the journey. The real superpower we've uncovered today lies in computational thinking, your ability to systematically break down the complexities of the world into structured, solvable steps. Which leaves us with one final exciting question for you. If programming is just translating intentions into solutions, what problem are you going to choose to solve first?